We're going to look at Lewis dot diagrams for compounds or simple compounds here. This is something we revisit at the very beginning of Chem 20. Let's look at drawing sodium sulfide. These are the first two examples in your notes. Sodium sulfide is an ionic compound because sodium is a metal and sulfide or sulfur is a nonmetal. This is ionic. Let's write its chemical formula. So sodium is a 1+, sulfur is a 2-. Therefore, I'm going to need 2 sodiums for every sulfur. We can verify this formula by drawing the ionic structure. So let's start with the atoms. We have a sodium atom and a sulfur atom. Sulfur has 6 electrons. Now, an ionic compound transfers electrons. So what happens is sodium and sulfur come near one another, and sulfur thinks, I would like more electrons to fill my octet. Sulfur is only 2 electrons away from a full octet. Sodium, however, is 7 electrons away from a full octet. Sodium would rather give up 1 electron than try and take 7 electrons from something else. So sodium gives away its electron to sulfur. Now, sulfur is a little bit closer to happy, but it's not totally stable yet. So, because there's not just ever one atom of an element present, a second sodium comes along. This second sodium also would rather give up 1 electron than gain 7. So it gives up its electron to sulfur as well. Now, sulfur has a full octet. We can draw sulfur with its new electrons. Sulfur now has 8 electrons. You don't need to draw the electrons that came from sodium any differently. Electrons all look the same. But we also have 2 sodiums as well. These sodiums don't have any electrons. It's really important to remember that when an element gives away electrons or accepts electrons, it's become an ion. To represent this as an ion, I need to include square brackets with its charge to represent a proper Lewis diagram. So the Lewis dot diagram for sodium sulfide looks something like this. We have 2 sodium ions attracted to 1 sulfur ion that is a 2-. One other way to write this is that I can write that we have 2 sodiums, and then we would draw sulfur as full. Remember, nonmetals have full octets, and it looks like sodium has an empty octet, but remembering that sodium has full core levels. It has 2 in the first level and 8 in the next level, and we just drew the 3rd shell as empty. Sodium is still happy. It technically has a full octet. It's just a little bit lower. Hydrosulfuric acid, let's draw its formula. Hydrosulfuric acid means a binary acid. A binary acid follows covalent bonding. So we need to write the molecular formula for this. Hydrosulfuric acid means that sulfur is present with a hydrogen. We actually balance it like an ionic compound, but we're going to draw it molecular. So we need 2 hydrogens for every 1 sulfur. Let's draw sulfur. Sulfur had 6 valence electrons, therefore we're going to draw it something like this. Remember that we pair only after we've gone around once. Hydrogen has 1 valence electron, and I'm going to draw it something like this. So in a covalent bond, we share electrons. There's no transfer. When we share, we create a bond. So we can share these 2 electrons. 2 electrons being shared makes a bond. These 2 electrons can also be shared, creating a bond. I can draw this as H with 2 electrons, 1 from hydrogen, 1 from sulfur, being shared to sulfur, and 1 electron from hydrogen down here and 1 electron from sulfur being shared to another hydrogen. Now this gets very complicated and looks a little bit messy when we have lots of electrons being shared. So what I like to do is once I've seen that we have paired our electrons here, I'm going to draw it, each pair of electrons as a bond. Okay, so one bond is actually 2 electrons being shared. Don't forget to add in sulfur's lone pairs. We must include those in our diagram. Notice how ionic bonds, there are no bonds actually drawn. We know that it is an attraction between a positive and a negative that is keeping these elements close together. In hydrosulfuric acid, we know that it's the sharing of 2 electrons that's keeping these together. Sharing 2 electrons, we draw bonds. Bonds appear in covalent compounds, not in ionic compounds. Why can the formula CaS2 be reduced to CaS, while C2H6 cannot be reduced to CH3? Use electron dot diagrams to support your answer. Well, calcium, if I draw 2 calcium ions and 2 sulfur atoms, I would have something like this. Calcium gives away its electrons to sulfur. What we see is that we actually only needed 1 sulfur atom and 1 calcium atom to complete the full transfer of electrons. Calcium is left with no electrons in its outer shell and is a 2+. Sulfur gained 2 electrons in its outer shell and became a 2-. I didn't need 2 sulfurs and 2 calciums to complete this full transfer. Therefore, calcium sulfate should be written as this, never with 2's. Remember, these 2's can be reduced. We divide each of these subscripts by 2 and we get calcium sulfate. This sometimes arises if you were doing the drop and cross method. C2H6, let's draw this one. In the end, we should have carbon with a carbon and 6 hydrogens. C2H6 is molecular, so we should be pairing their electrons to share. We should be able to share electrons quite easily like this. Now this looks complex. So remember, 2 electrons being shared between 2 elements can be written as a bond. I'm going to draw these as bonds. Every atom in this compound has a full octet. Carbon has 8 electrons, 2, 4, 6, 8 electrons being shared around it. You can also count in our original diagram, 2, 4, 6, 8 electrons. This carbon also has 8 electrons, 2, 4, 6, 8, or 2, 4, 6, 8. Remember, hydrogen doesn't want 8 electrons. It only wants 2. So one bond will do it. 2 electrons around each hydrogen in our diagrams. So everybody's happy with their octets. If I were to draw CH3, remember carbon has 4 unpaired electrons, hydrogen each has 1. If we look to join these, I have an electron that's all by itself. Let's draw this. So carbon bonded to a hydrogen, bonded to a hydrogen, bonded to a hydrogen, and 1 unpaired electron. This is really unhappy for carbon. Carbon is the element most likely to never, ever, ever have an unpaired electron. They do exist in nature, but not really for carbon. Carbon gets so angry about this one unpaired electron that it'll attack pretty much any other element with valence electrons and force it to bond. So it will seek out anything else to bond with at this point. We cannot have unpaired electrons. So Ca2S2 can be reduced to calcium sulfide because we only needed that one calcium and one sulfur to transfer all of electrons to get a full octet. C2H6, when we drew it out, everybody had a full octet and was fully bonded. There were no lone electrons. When I draw CH3 though, trying to reduce the 2 and the 6, I'm left with this unpaired electron that makes carbon so unhappy, the angriest element ever, it will go attack anything to pair up its electron, thus changing the chemical formula because it will have reacted with something else. There's some practice for drawing Lewis diagrams or Lewis structures or electron dot diagrams, whatever you want to call them, for some simple compounds in your booklet.